Today, we're diving into one of the most incredible feats of human engineering ever, the microchip. Seriously, how do we build these tiny little universes of logic with billions, and I mean billions, of parts all on a tiny sliver of silicon? Let's get into it.
First off, we've really got to get our heads around the sheer scale we're talking about here. You've probably heard the term billions of transistors thrown around, but what does that actually look like? It's one thing to say the number, it's another thing to see it. Okay, take a look at this. Now, that is not an aerial photo of some sprawling metropolis. That's a microchip, specifically an Intel Pentium 4 from the early 2000s. And get this, it has over 42 million transistors, and that's ancient. Today's chips have billions. It just looks impossibly complex, right? Well, that's because it is. So you gotta wonder, how did we get from here to that? Well, the very first microprocessors were basically works of art. I mean, engineers would literally draw and lay out every single transistor by hand. It was this careful, painstaking, almost artisanal process. But you can see how that just doesn't scale. You can't handcraft something with millions, let alone billions of components. No way. And that really brings us to the core mystery here. How in the world is this possible? How do you go from a blank piece of silicon to this perfectly functioning city with billions of parts, where just one tiny mistake, one misplaced connection, could render the entire thing useless? The answer, like with a lot of brilliant engineering, starts by thinking really, really small. We have to zoom way in, past all the city blocks and highways of the chip, all the way down to the single most fundamental building block of this entire digital universe. And here it is, the transistor. For all the complexity we just saw, it all boils down to this one incredibly simple idea. A transistor is just a switch, a microscopic switch. It can be on or it can be off. That's it. That's the whole game. Every single thing your computer does, from opening a file to rendering some crazy 3D graphic, is just the result of flipping billions of these little guys on and off at insane speeds. And this is where the magic really starts. That simple physical state, on or off, maps directly to the language of computers, binary. When a transistor is off, we call that a 0. When it's on, we call that a 1. And there you have it. That is the foundation of, well, everything digital. Okay, so we've got billions of tiny switches. That's great. But a giant pile of switches isn't a computer, right? The real genius is how you organize them all. How do you tame billions of anything and get them to work together to do something useful? The secret, the absolute key to all of this, is a powerful concept called abstraction. You can think of it as a divide and conquer strategy. Instead of trying to think about billions of switches all at once, which would literally break your brain, designers think in layers. So let's build this up layer by layer so you can see what I mean. At the very bottom, level 1, we have the device. This is our humble little transistor, the on-off switch we just talked about. The job of an engineer at this level is just to make this one switch as perfect as possible. Then we move up to level 2, the gate. Here, we take a few of those perfect little switches and wire them together to create something new, a logic gate. A good example is an AND gate. It's pretty simple. It only outputs a 1 if its first input and its second input are both 1. So suddenly, we've created a new, slightly smarter building block. Moving on up to level 3, we get to the module. Now we're taking those logic gates and combining them to create black boxes that do useful things, like an adder that can, you guess it, add two numbers together. And here's the crucial part. A designer working at this level doesn't need to know about the transistors or gates inside. They just trust that the adder black box works. And finally, at the very top, level 4, we have the system. Here, you're taking all those useful black boxes, adders, memory controllers, you name it, and you're plugging them together like giant Lego blocks to build the entire processor. The system architect up here isn't thinking about individual transistors. They're working with these big, functional blocks. Each layer completely hides the mind-numbing complexity of the layer below it. That's abstraction. This quote just nails the analogy. It's exactly like writing software. A programmer doesn't need to know how the file open command physically moved the little head on the hard drive to find the data. They just use the command and trust it works. Chip designers do the exact same thing with their modules. Abstraction is the only reason any of this is possible.
So, That's the design philosophy, the master plan. But how do you physically build something with parts so small you can't even see them with a normal microscope? You're not using tiny robots. The answer is way cooler. You basically print it with light.
The process is called photolithography. It sounds complicated, but think of it like screen printing a t-shirt, but on a microscopic scale. You start with a pure silicon disc, that's the wafer, and you coat it with a light-sensitive chemical. Then you shine ultraviolet light through a stencil, which is called a mask. Everywhere the light hits, the chemical hardens, you wash away the soft parts, and then you can etch a pattern into the silicon underneath. You just repeat this process over and over with dozens of different masks, building the chip up one tiny layer at a time. And when I say stencil or mask, this is what the blueprint for it looks like. It's called a layout, and it is an incredibly detailed plan for just one of those dozens of layers. This exact pattern gets shrunk down and projected onto the wafer, defining exactly where all the transistors and wires for that layer are going to be formed. So we've got a design plan, abstraction. We've got a manufacturing process, photolithography. So we're all set, right? Not quite. This is where the real struggle begins for chip designers, because every single one of them is fighting a constant battle between competing goals. You're essentially juggling these four things. You need the chip to be cheap. You need it to be fast, that's performance. You need it to sip power, not guzzle it. And of course, you need it to be reliable. The problem? These four goals basically hate each other. If you try to make a chip faster, it almost always uses more power. If you make it more robust, it probably gets bigger, which makes it way more expensive. It is a constant, frustrating balancing act. But of all those competing factors, one of them is the absolute king when it comes to cost. And that is simply the physical area of the chip. How much space does it take up on that silicon wafer? Smaller is always, always cheaper. Why? Simple economics. The smaller your chip is, the more of them you can cram onto a single wafer, and the higher the chances that they'll work perfectly without any tiny defects. And the relationship between a chip size and its cost isn't just a straight line. It is, as the quote says, brutal. The cost is roughly proportional to the area to the fourth power. Let me translate that for you. That means making your chip just a tiny bit bigger doesn't make it a tiny bit more expensive. It makes it massively more expensive. This is the harsh economic reality that drives the entire industry's relentless obsession with making things smaller. And that leads us with one last fascinating thought for the future. For decades, the entire game was about making the transistor, the switch, smaller and faster. And we got incredibly good at it. But now we've packed so many of them so densely that the bottleneck isn't the switch anymore. It's the wires connecting them. The signals are getting stuck in traffic on these tiny copper roads. So the question for the next generation of designers is this: how do you solve a traffic jam when the roads themselves are the problem? And that's the challenge that's going to define the future of computing.